I'd like to move on and introduce to you Justin Brackenrich, who is with the College of Agricultural Sciences, Penn State Extension. And if you were in Pennsylvania, Pittsburgh, and Butler County last October for the TOPCORP training, you would have had an opportunity to meet Justin because he was out on our technical field trip at the soil pits. And he and Tom Murphy were the people, our resident experts, who talked about what was going on in those soil pits and getting to see firsthand what the undisturbed versus disturbed soil profile looks like. So with that, it's a pleasure to introduce to you Justin Brackenrich. And again, if you would put your questions in the Q&A pod, Justin will attack those at the end of the presentation. So with that, Justin, thanks for being with us, and I'll stop sharing my screen and turn it over to you.
Okay, thanks, John. Let me get mine shared. Okay, that should be correct. You should be seeing this now. Let me move this over. Okay.
Looks good.
Okay, very good. Thank you guys for being here. And I have to say, I told John before this started that this is probably the most nervous I've been to give a talk for a while, because looking at the registration list of everybody being spread out and all over the country, and your affiliations to different governmental departments and universities and regulatory agents, it's pretty overwhelming to think of being someone to educate you folks. And so, you know, I thank John for having the confidence in me to give this, and I thank you guys for giving me the time to speak with you on this. So, you know, a little bit about me is I started my agronomy and part of my position in reclamation at WVU, and I worked there on my master's degree and trained there with some doctors there that worked more on acid mine drainage and the reclamation of coal mines. And so that was kind of where I got involved in some of this. And then as I moved up here to Butler, which would be just north of Pittsburgh, I got involved more in the aftermath of pipelines. So we don't have as many active pipelines here now as what we did, but what I deal with is more in the renovation and the people that are coming back in and trying to farm after the pipeline or the well pad has been done, and what we could do, you know, if it was to come back and have a different opportunity to redo something, or how we could have seeded this a little different to, you know, change what happens here over the course of time, and how we could have healed some of this soil. So I kind of want to give a little bit of a disclaimer, is that, you know, please don't take me as an engineer or telling you folks how to do your jobs. That's certainly not my intention, because I don't understand what you do as far as the engineering component goes of the compaction that you need to make sure these pipelines are stable and that things are going to drain and work properly. But what I do understand are these final steps and the compaction that we need, and the layers of topsoil and the layers of subsoil that we need, and how we can aggregate this stuff to go back to growing crops, or return to somewhat of an original profitability for these producers. And so I just want to make sure that you're not taking this as, you know, this guy's telling me how to do my job. It's not that. I'm just trying to kind of look at this from a standpoint of someone that can help kind of keep relations maybe a little bit better with the producer that you're working with, and also getting some vegetation back on those sites in a little bit different way. So what I want to look at first is talking about soil profiles. You know, that was what we looked at the TOPCORP training in the field, is a disturbed profile versus an undisturbed profile, and how that can really affect the drainage that we see. And I know that does affect how you guys can do your work. And then the pH issues and the fertility that come along with this disturbance that are there, because that is very crucial to reestablishing the seeding and any subsequent crops that occur there. I want to take a quick minute to look at some rooting issues that we get after this surface compaction and some subsurface compaction that come in these pipeline or these right-of-way adjacent areas, and then how that translates itself into a depressed yield, or the limitation that we have to really develop these crops, or even get just a seed, or even if we're looking at just seeding down some ryegrass or something to grow to make this site green and pass inspection. And then lastly, I want to look at the species selections that we can use if we're talking about planting something long-term versus short-term, and how we can manage this with some of these concerns, right? So we're going to look at some nutrient deficiencies and talk about the NP and the K levels in the soil. And then if we're coming back to look and we say this site isn't performing well, can we address some of these from a hunger sign in these crops and make a view at that as to maybe why we're seeing a lack of vegetation. So as we're all, and I think of, we had some Canadian friends that were there. We looked at some people from Texas. Oh yeah, and I did forget. So I'm in Butler, and again, that's north of Pittsburgh. I am 57 degrees, have a 8-mile-an-hour wind coming out of the southwest, and it is misting rain. So about as miserable as a day that you could possibly ask for. But if you're giving a webinar and you're sitting in your house, it's kind of perfect for that. So makes me pretty jealous of the people that were looking at 75 and sunny. So anyway, but all of these profiles are not equal, right? So we think of the people that are in the southern areas that would have more of a sandy profile. As we move north into northern Pennsylvania or New England, these more glaciated areas that are going to have a heavier clay, more of a mucky kind of a substance. How is that going to affect what we're doing, right? So from you guys and your standpoint, if you're going out and you're viewing something, or you're doing a site assessment, you know just how that changes the amount of work you can do, and how a spill is handled or runoff, and the amount of settling ponds you have to have changes. And then after that, right, once you put this stuff back, how well is it going to drain? Is it going to be fertile or not? Because if it wasn't fertile before, it's certainly not going to be after we put it back. And so we need to address that. And then also, was this going through forested area, or was this going through farmed area? Is this close to urban? Is this rural land? And all of that does have a way of kind of manifesting itself into something else. I apologize. I forgot to sign out on my telephone. I had a checklist and I missed one. So from a profile standpoint, right, these are things, I'm looking for my pointer, laser pointer. So these are all profiles that are essentially the same amount of depth. And this would be something more typical of a southern, more of a clay profile. If you look at that, you can almost see the granulation that would be in there from all of the clay. We can see a deeper topsoil here and very smooth transitions as we go from something of topsoil into a B layer and even into a C. But the strata does not look to be different. It looks very tight. This is going to be something more of an alluvial type soil that's going to have some clay in it. It's very gleyed, so we can tell that this is fairly inundated often. And so we're seeing oxidations, meaning that since this is holding water, a lot of these irons are starting to rust essentially inside the soil. And so this surface, this pit that we're looking at, can kind of tell us, okay, this is going to be very wet. This is more of a southern, kind of southern West Virginia and South soil of being very red. And so we have a very tilled top layer that's going to be very homogeneous. We move south, and we really can't depict where we would move from a B to a C horizon. But we do know there's a lot of irons in there that are going to cause that pH to be very, very low, right? We're going to be looking at pHs into the 4s, even, moving up into the 5s. But this is more typical of what we're going to see in Pennsylvania. We're going to see a bedrock somewhere that's going to be around 30 inches. We're going to see some typical kind of unconsolidated rock spread out. We're going to see a classic B subsoil here with some channery stuff, and then more of a developed A horizon that could be anywhere between 2 to 6 inches. But as you know, when you're working with big equipment, and we start talking about putting things back, no matter what method we do, when we have 3 inches of topsoil, how can you accurately and reasonably scrape 3 inches of soil off, store that somewhere else, and then put 3 inches right back on top, right? That becomes very difficult to do. And so we're looking at it, obviously we're going to have to get some mixing action happening there. And so through that process, how can we treat that then to get this to work? So This is all formation of our soil genesis, right? So this is the overlaying thing of pedology. And I saw some geologists on here, and it's, you know, I don't claim to be a soil scientist, right? If you're a geologist or you're a soil scientist, we know that it's all very different disciplines, right? An agronomist is not a soil scientist and vice versa. We have all very different disciplines, but we do have to have a little bit of knowledge that overlaps. And so what we look at is this parent material, right? Where are we actually working? Are we in Appalachia, where this is an old situation where we've had the time to weather these soils and weather this bedrock? What's our climate like? Are we somewhere up here where we're going to be getting, you know, 40 to 50 inches of rain and snow a year? Are you somewhere in Texas that's going to have half of that, if not a third? Where are we at on our topography? If we're moving to the top of the slope, we're likely going to see less soil and we're going to get to rock quicker due to erosive properties, versus being at a toe slope where we're going to have collected the majority of this soil over years of washing downward. And so again, all of that's going to factor into how we can reclaim this, how we know we have to store it, and how our methods are going to result in a final product. Again, briefly on horizons, maybe this one should have been a little further up, but we have these kind of master classes, right? We have an O, which we translate to the organic material that's just the top, right? That's that very skinny layer across the top, unless you're more towards the Midwest, where these O horizons can be very deep in our prairies. We have our A, which is our topsoil that contains a lot of that organic matter. Then we move into our B's and our C's, which are classified as subsoil. So that's where it's going to get tighter with those clays. And then R, which is what we consider bedrock or restrictive. And so with you guys, right, with the heavy machinery, restrictive takes on a much different term. And so we don't look at that generally as something for us or for you in that construction business as being restrictive. That's much different. We look at that restricted as, is that restrictive to water? Is that restrictive to air? Is that restrictive to plant movement? And so that's what we're looking at when we develop these kind of profiles. So running through a couple profiles, this is kind of a glaciated profile that would have came from UMass campus. And again, this AP, this small p, denotes a plow layer. And this plow layer means that it's going to be very homogeneous. It's going to be mixed. We're not going to see a lot of structure in here. And so our infiltration of this is going to be much different, meaning that it's going to be cropped. It's going to be, it would have been cropped at some point in time. And we go back into these B's and C's, meaning our subsoils, of a layer that's going to split somewhere around here. But we go back to this term of glade, meaning that it's often inundated with water, and we're seeing this oxidation occurring somewhere in here in these gray colors. And so again, when we start thinking about growing crops, or we start looking at changing this hydrology and adjusting this water table, if we have some kind of a contract or stipulation that we need to put back something here, we're probably not going to want to sign something, or we're not going to want to go back into alfalfa here because we've disrupted this. Corn is probably not going to be something good here. Some sort of a small grain is probably not going to perform here because they don't like the water. What we have to do is be aware of this before, because anything that happens before is likely going to persist as we come back. Even though we're changing that, as we've unconsolidated, it's going to present a whole new set of changes. But if we have water before, we will find that water later in time. So this is a glacial till kind of a deposit. So this is something that's more familiar to this area. I saw some people around Clarion and north of here. Again, we see this A horizon, this top. We move down into a B and a W, meaning they're weak, so they're not going to be very structured. And C's and D's, this D indicates it's dense, and so that's where we're going to start to see that restriction. This is not a very deep soil. And so again, this gets back into, how do we separate this? How do we get a topsoil off when it's, you know, essentially 4 inches deep? And that's what we're left to work with when we have to put this all back and then develop a crop on top of it. It becomes very tedious. And so we have to know what we're working with to continue to maintain. Soil texture plays a big part of this as we look at soil texture. So this is defined as particle size that's going to be less than 2 millimeters. If it's greater than 2 millimeters, that's generally a coarse fragment that we're going to consider part of like a channery a small rock particle. And how this breaks down is we think about the soil particles as visually, let's think about a piece of sand as a beach ball. And then we drop in size to a piece of silt that may be the size of a tennis ball and a piece of clay that's going to be the size of a marble. And that results basically in surface area. And those surface areas yield to porosity in that soil. It yields to our ability to hold nutrients. It yields our ability to keep water, keep air, support the life of macro flora and fauna. And so if you were to take a cylinder and fill it full of tennis balls, the pores would be much, much larger. But if you took the pores of the same cylinder and filled it full of marbles, your pores are going to be a very different size, but you're going to have a much larger amount of surface area there. And when we start thinking about sticking nutrients, these small elements and these small molecules, we need surface area. And that's where this terminology of a cation exchange capacity comes from, and our ability to hold nutrients within these soils. That cation exchange capacity, we look at this from clays moving down to sand. And so as a sand particle being that volleyball or that beach ball, there's not as much surface area there. And so we can't hold as many of these nutrients compared to clay, right? So in that cylinder of marbles, we can fit a lot more nutrients there. And so that, again, that's going to derive as to our ability to return some of these things back and support what we can do there. And I deal with farmers here that work with a lot of clay. And when I was in West Virginia, we worked with a lot of clay, and they say, boy, it'd be nice to not have these heavy, these really wet soils. But you start working with sandy soils, and we see this over in the Delmarva and areas where we have a lot of leaching, is nutrient retention becomes very, very difficult when you put a nutrient down and your leaching capacity is tremendous because you have nothing to hold. And so everything has its double-edged sword, right? So we don't have water retention, we don't have this issue of ponding, but it becomes very, very difficult to get nutrients there, and the right timing of these applications truly becomes our critical point to make sure we're not wasting. CEC and in our removal in here then leads us to acidity. As we go in and we start to remove a lot of this material off, even the removal of plant biomass, as we remove this, what we start to see is this loss of these base cations, and that can lead to an increased soil acidity. And when we pull these out and we take these microorganisms and these plants, they're going to start to respire, and they're going to start to die, and that release of CO2 can lead to a carbonic acid buildup. And so whether we're looking at the topsoil or we're looking at this subsoil that may inherently already be very acidic, we can't just take this back and put it on there and then expect something to grow, because we've kind of made this happen by moving it. The same with nitrification. As we move stuff out of these soils, as we disrupt that soil's natural environment, what we do is we cause this ammonium to want to bond with the oxygen that we're pulling up out of the air because it's stored in a pile. It's going to create nitrate and this addition of hydrogen, which then acidifies our soil on their own. And so when we're leaving these things out in water, we're leaving them in cooler temperatures, we can then acidify things. So that's where it's really important to kind of know this morphology and know this parent material and look at these soil pits to have an idea of, okay, so this is what we've done and what we're going to do. But when we start to put this back, what steps do we really need to kind of look at to make sure we can establish something? Because I know John and I spoke briefly before we started, is sometimes the responsibility is to have something green. And that's the regulation. But sometimes we want to take that a step further, and we want to go to what can we plant back that's going to not only give us something green, but something that's going to foster a good relationship with that producer. And so we want to make sure that we're doing the best we can with that, right? No one wants to get into this kind of a situation and spend a bunch of money and put a bunch of seed down, and then you walk away from it, and 6 months later, either nothing has grown because our soil is too acidic or it's too wet, when we could have known some of this was going to occur, and we planted something like a cereal rye that now is dead because it's wet. Or we didn't know that it was going to be this acidic. And so we went out and we bought this mix that was 35 or 40% alfalfa. And now we've got a very acid soil, and the alfalfa didn't grow. These are the things that we can glean from looking at a lot of these soil profiles and discussing some of these physical properties that then lend themselves to more of our chemical properties. So looking at compaction, again, this is compaction on site adjacent topsoil type stuff, not compaction around the piping itself or that sort of thing that you need for your stability. But one of the really things that we'll get into is looking at compaction and nutrient movement. And so this is corn, and phosphorus has a very characteristic purple color when we're in a deficit of phosphorus. And so anytime you see, whether it's a grass or a tomato plant or anything that has this purplish color, that's a lack of phosphorus. And phosphorus is fairly immobile in our soils because it gets held very tightly when you're talking about clays. Now, somewhere where you're looking at more sandy soils, the orthophosphates can move because of that low CEC. But if you see that purplish color and you know that you have phosphorus in your soil, 9 times out of 10, that's going to be a result of a compaction problem. Looking at this one on the right, you can see really distinctively that there's a tracks that kind of run through here. And we'll pull back to this and look at it moving forward a little bit. But that's a characteristic of compaction where we had vehicles moving through this field, and right now it's purple dead nettle, but it still will result in it. And if I could fast forward 6 months or even 3 months and show you the corn that's going to be planted in here, there will be a height difference based on that surface compaction in this field. So what is soil compaction, right? So I'm sure you all know, but it's a compression of these particles resulting in a change of volume that we get from an outside force. And it's going to be classified as either surface or subsurface. And so from an agricultural standpoint, and what we look at is it's generally going to be done on surface or subsurface, and what we can change to kind of back both of those off. And so we have causes, right? Everything has a cause, everything has an effect. We have things that we can't really control, right? So the condition of the soil, we want to avoid movement when it's wet. When we get to that plastic state, when the soil begins to flow, when we can squeeze it and get water out, that's when we're very, very susceptible. Right to that point of being moist and being plastic is where we're so very close and so very concerned with compaction. Parent material on its own and that surface texture on its own is going to be something that can lead to compaction without any other conditions. Is if you're trying to compact clay, right? If you go to the beach and you try and build a sandcastle, it's almost impossible to get that bucket to turn upside and dump out no matter how hard you push without the top corner breaking off. If you go down to the edge of the pond and you pull out clay and you pack it in there, you can't get it out of the bucket because it compacts. That's really erroneous to whatever you do on your job site. That's just a relationship of the compacted soil based on what its parent material was. From our equipment standpoint, we talk about rubber tires. We still have to use rubber tires, but we throw in flotation tires in the mix compared to using radials or really high PSI tires. And weights of equipment over the last 30 years or 20 years, whatever we want to look at. You guys would have better knowledge on your equipment than I would, but we've pushed our equipment to be heavier because it wants to be more efficient. We want to move more rock. We want to increase our work. And so while we do that, we're also making higher pressure points. And then lastly is our farming practices. Tillage is often what we think of as, I'm going to do a much better job and I'm going to relieve this compaction, so let me go out here and till it. But that's almost like rubbing salt in a wound. Is when something is compacted, to loosen that up is because you're basically taking the pieces of a puzzle that have been put together, you're lifting those fragments and those pieces, and then you're allowing another force to come right back over top of them and pack them back down again. And then lastly, if you're working somewhere where you're hauling manure or fertilizer or lime, those axle weights, again, can be very heavy. And so sometimes this is not stuff within our control. So as we look at surface compaction, so surface compaction is often controlled with the axle load. Excuse me, subsurface compaction is controlled by axle load. When we look at a 5-ton or less axle load on the same tire width, what we can get is we're going to move through the topsoil and into, about a 15-inch depth. When we start to bump into this high load of 10 tons or more per axle, that's when we can push down into the 25, 28, 30-inch depth, because we're no longer talking about the footprint, but more of that vertical weight just pushing down into these soils. And so that's where we try and reduce our load per axle. We try and spread that out by using things like duals. We try to look at tracks, and we try to add more axles to the program. When we look at subsurface or surface compaction, flotation device tires, if we're doing tracks, we can spread that out so we're not getting as much footprint. We're getting more footprint. But what we see is if we have a high axle load, that 10 tons plus on a flotation tire versus a narrow tire, we get the same amount of depth on our subsurface compaction. We get the same amount of stress peak, 11 psi's at 22 inches. But when we start to look at that topsoil, we have much less on the flotation compared to the high axle load on a narrow tire. And so we can change the subsurface, but that deeper stress that we get on subsurface is really not going to change when we get into these very high loads. Again, that's pushing our axle strength. And so back to this one, we looked at this, and the reason that this exists is it was a manure hauling operation. And so they were trying to get back over into here, and they couldn't swing the turn. And so they would come in and they would swing this. And so this repetitive motion of 5,000 gallons of manure plus equipment were somewhere around 9-10 tons per axle that they had. And I went out and I took my penetrometer, and we're going to talk a little bit more about that. And over in here, I was reading less than 100 pounds per square inch, and over in here was the same. But when we moved into this area, that pressure in that subsurface reading was, so we were right at that breaking point, right at that 15-inch mark. We were pushing into the 150 to 250 pounds per square inch to get through that restrictive layer. And so, yeah, we have less plants on the top just because they were killed by the trauma and the weight. But again, there is a tremendous amount of compaction in here that'll manifest itself. So a penetrometer, this is the analytical scientific way to measure compaction. You can buy these relatively cheap. They're less than $200. And so what they are is they're designed to mimic a plant root. They have 2 tips on them. And they have a 30-degree point. And that 30 degrees is designed to be that lead tip, the same as what a plant would have. And one's for sandier soils. It's a larger tip to put up more resistance compared to a smaller one that we would use more in the clay regions or the siltier regions. And they're monitoring a PSI. So if we were using in the sandier soils this larger tip, we're going to run this up to this 300 PSI is going to be this maximum reading, compared to the smaller tip would be in here. And so we've got increments of 3 inches on this stainless steel line. And so I thought about bringing my penetrometer in and switching off the camera and trying to stand in here or stand on my chair or something and show you guys with it, because they are very, very interesting to play with. If you've used one and you were at the TOPCORP training, we had them, and you can read the PSI to get the PSI, but you can also, if you've used one, you can feel it in the pressure that you apply, right? You can move very slowly down, and you can feel this very gradual resistance. All of a sudden you notice in your shoulders that you have to start pushing more and more, and then all of a sudden it breaks off because you're much stronger than that 300 PSI that you can put on that pointed tip. And so from a root penetration standpoint, at 300 PSI, we see 0 root penetration. And what that means is we're not going to penetrate. So, I'll visualize that if the root's coming downward, it won't penetrate that surface at 300 PSI. What it'll do is it'll turn and run laterally and look for a crack. And so it's not saying that if we get to 300 psi, it's going to die. What it's saying is now what we will do is if you were to dig that up and look at those plants, you're going to find a whole bunch of a mess of these mats where these roots have come down and then they flattened out and ran laterally to make through that crack somewhere, whether that be just a natural split, whether it be a wormhole, whatever the case may be, they're going to look for a natural groove. And we can see depletion in these root penetrations anywhere between 80 and 300 psi. So it doesn't take very much to get there. So from a subsurface compaction comparison here, this was a study that was looking at long-term effect of subsurface. And what they looked at was so at 0 years, they had about an 85% relative yield. And it took essentially 5 years to get up here to about this 92 something yield. And then to be up to the 10 years to get closer to this 100% yield. Because subsurface compaction is not nearly as dramatic. We're not going to see this really stunted growth. It's not like the corn to the left and right are going to be 9 feet tall and the corn that's in this subsurface compaction is going to be 4 feet tall. What we're going to see is this incremental decrease, this 15%, this 12% decrease. And we can't fix that one short term. When we talk about the severity of a surface compaction, that's going to be very severe, but we can loosen that up quickly. Whether we put in some grasses or a cover crop, or we use the freeze-thaw cycle and the shrink-swell of our clays, that's going to loosen up that surface compaction. But when we start looking at this subsurface, we have this increased bulk density, right? So the volume has decreased, and we have a much heavier soil, which is going to decrease our water depth at that level where those deeper tap roots are. We're going to have more increase of our runoff, and so we're not going to be getting that infiltration. And we're going to have decrease to this plant health and cover, which is going to cause more surface compaction due to rain events. It's going to cause more erosion and runoff, and we're just not going to see the performance that we want. So this was a test where they had root growth. You can see some of the comparison here, how it kind of whips its way through there. And what they did was they did a subsurface compaction right here between this surface and subsurface zone, and then looked at the roots and what happened. And so originally, roots were filling in a lot of this void space. And as this was compacted, these roots became very fragmented. They were no longer allowed to go in there and fill these spaces, and they began to find channels, straight down this edge where they couldn't get the compaction because it was in this compressed box. And the roots just became very segmented, and that root growth was restricted. And so that began to lead to this stunted growth and a lack of yield in these crops. And so we not only see stunted growth because of the roots, but we see stunted growth because of that limited nutrient availability. And as we start to think about, so this was looking at nitrogen on corn, we had a bulk density. So if you're not familiar, that's looking at the volume of the grams of soils per volume. And the higher the number, the tighter the volume of that soil, the higher the bulk density, the more soil you're going to have in a known volume, and the more compacted the soil is. And so where we had this 1.55 grams, we were not able to retain as much of that nutrient. It wasn't able to go out and get it because these roots, right? So this is a typical corn plant through its genesis into, V1, vegetative 1 stage of its life cycle. These are very, very small roots. They're running very, very laterally through this top. And as we look at, if we have bulk density issues here, if we have surface compaction, we're not sending deep roots at this point. We're sending lateral roots that if we can't get them through that surface, we're not going to be able to get the nutrients that we need, and we're not going to be able to pick them up for the growth and the development of any of these plants, regardless of if it's a legume, if it's a grass, if it's a brassica, if it's an annual, or regardless of that fact. So if we have compaction, from a subsoil standpoint, we want to reduce our load weights, and we want to increase the number of axils that we have. From a subsoil, we really don't want to try and get in there in subsoil. I mentioned this a little bit later or earlier on, that relief that we're going to see by subsoiling on these top parts where we're kind of finishing this stuff up in reclamation, it's going to loosen that soil up. But then as soon as we start going back out there and doing any more field work, that's just going to fit all of those pieces of that puzzle right back together. And so the saying is that roots are much better than iron when it comes to relieving compaction, because you'll see if you subsoil, you're going to have to do it once. And then if you stop for a year, you're going to notice this dramatic decrease. And then they're going to have to do it again and again and again and again. Whereas with roots and incorporating better vegetation, we can make this work for us in a way that we're going to steadily increase, not having to continue to do this or decrease. So what do, right? We get something growing. The growing is going to help us reduce erosion, it's going to help us increase this soil structure. We're going to be able to get some organic matter back on this site, which is going to help with that structure and going to help with some water. And we're going to help to relieve that subsurface compaction. These are the things that we're all looking to do, whether your job is just to get something growing, or whether your job is to get something there for the producer that they can use for long term. Regardless of that, we need it to grow, right? That's how we have to leave this site. And so the first thing I would want you to see anybody do is to get a soil test. Going out, taking a sample of that soil, going out to test it is pretty simple. Sending it off, getting an analytical value. If nothing else, you have some data to show the landowner that you worked on is that, hey, look, this soil will grow. We aren't leaving a poor pH. We've got good NP and K levels here. The magnesium is sufficient. So if you're grazing animals, you shouldn't have a concern. And that's good information for anyone to really have to share with someone like that. And they're relatively inexpensive. I can't speak to other places, but I know in the Mid-Atlantic, you're looking at $15 or less for a soil sample. So I would also comment that if you're in the Pennsylvania or the Mid-Atlantic region, you're likely going to need lime, because if you've dug up any of this subsoil, if you've left this stuff sit out there, it's going to have acidified. You're going to have found some irons and some aluminums in there. You may not need the fertilizer, but I would certainly recommend that you'll probably need to lime this to get some establishment. So I want to run through a little bit about each of these nutrients that we have and how we can kind of diagnose, right? So if you do go out and you plant, and even if you're just planting an annual crop and you say, okay, I threw out a bunch of rye, we hydro-seeded rye, it didn't grow, why not? What do we need to do to make this better? These are some diagnostic visual symptoms of what we can do to make this work. So nitrogen is the thing that we require most in our plants. More than any other element, we're going to absorb nitrogen. And we use nitrogen as nitrate, and we use it as ammonium. And if you're versed in your chemical properties, you can recognize that ammonium and nitrate are two of the most difficult chemicals, molecules to work with in about any environment that we have naturally occurring, because nitrate is a negative charge and will carry itself away with water. And ammonium has an affinity to do about anything it wants to, including turn to a gas or turn back into an inorganic form, which is essentially useless to a plant. And so plants use this to produce chlorophyll and protein, and they use it in their RNA and DNA. And so if you go out and you're looking at this, you're going to see a really lush plant. It's going to be growing rapidly. It's going to be dark green. It's going to have a good protein content. You're going to see it drawing up water, and you're going to be able to use your other nutrients better. One of the things that we can do if we're looking at really big wet spots in fields, or you know that you're going to have some drainage issues, we can promote this with looking at things like a reed canary grass, or another type of a grass that may draw a lot of water. And so if we can get good nitrogen management on something like that, then that's going to help us suck up water and get it out of some of these places, so that we're not having these wet spots or some of these swales full of water that we have to deal with. We can just turn it into grass. And so from a negative side, and we don't have enough nitrogen, what we notice is we're going to lack plant vigor, but we're going to see this chlorosis first. And it's going to be this death, this yellowing in leaves. And so nitrogen is mobile. It's one of the mobile elements within a plant. And so what they'll do is their affinity is to want to grow upward. And so they will take the nitrogen out of the chlorophyll, out of the plant leaves that are oldest, and they will move that from these leaves down here, from these leaves here, back up and into these newer, greener leaves where they can collect more sunshine. Excuse me. So if you're looking at grasses that you've planted, if you're looking at, somewhere where you did a native habitat or planting, if you're looking at trees, anytime you start to see yellowing on older leaves, but not on the new growth, that is a very good indication that you're lacking nitrogen. Now, that nitrogen lack could be because if you're seeing standing water, you could be going through a denitrification process. You could have other responses that it's not necessarily lacking in the environment. It just may be lacking in the plant. So what do? We need to get the nitrogen on when the plant needs it. And so if we're really cutting it close, right? If we're trying to finish a project up in, say, September, October, that's not going to be our best time to put nitrogen on, right? So I'm speaking from Pennsylvania, right? Maybe if you're in Texas or Oklahoma, your growing season may be different than us. I know in the upper Midwest, it still gets fairly cold. And I know down in Oklahoma and Missouri, you can still get cold as well. But you want to get that nitrogen on when the plant can use it, because if not, it's going to disappear, right? It's going to be lost in the environment. And then we're going to see water quality concerns. And so timing is so important to that nitrogen application. Nitrogen is less important to the development of a starting plant. When we really want to see that nitrogen on is when that plant is 4 to 6 inches tall, not so much at root development, but more so later on in its life. Phosphorus. So in our natural systems, phosphorus is generally the plant nutrient that we lack the most, because we've weathered our soils such to a point that we've lost them. And so we absorb these things as orthophosphates. And again, you notice that they both have a negative charge. And the majority of what we have in our soils as cations would have a positive charge. And so it becomes very difficult for us to always contain negative charges within soils. And so if you're familiar with very sandy soils or things around the Delta or the Chesapeake Bay, you know that orthophosphates can be mobile in certain situations. However, they don't really like to move in the soil when it's very clay or it's very tight. But in certain situations, we can move orthophosphates quickly. And so they're going to be used in cell membranes and building strong cell walls. And if you've ever heard of ATP, which is an energy source, that's where we use a lot of phosphorus in the plant. So if they look good, if we've got a lot of phosphorus, they're going to start quickly. You're going to see a healthy plant, right? So it's very important to establishing your crop. If you're going out and you're going to plant something, make sure your phosphorus concentrations are right in the soil. That regardless of if you're broadcasting or drilling something, we need good phosphorus, because that's going to help us take up water. That's going to help us take up nitrogen and potassium. And again, if we're looking at pushing the envelope towards the end of the year, the phosphorus is going to help this plant be more cold tolerant. A lot of times we look at adding phosphorus and potassium to our plants in the fall to give them a stronger wintering, to give them an earlier bounce back in the spring. And it really, really helps to manage that so that when the spring comes around, we have a better growing, a more vigorous plant for cover. So again, I mentioned this, we'll see stunted plants, but there's that purpling again, right? That's the purpling here along the edges. This is a more severe case because this plant is older in its life cycle, and this is a newer one. But again, we either see that as a deficiency, but a lot of times that is a symptom of compaction. Because the phosphorus isn't going to move that much within the soil unless it's very sandy. So phosphorus is one of these elements that won't be taken up rapidly in the soil. And so when we put it down, we're going to have to recognize that we only get about 10 to 20% our first year. And so placement is very important. We have to get it where we want it. And that's why in a lot of agricultural practices, we can band this and we can put it as near to the seed as possible to increase this efficiency. And so in this case, where we would be broadcasting and using a broadcast application, we would want to make sure that we were getting enough of it on to meet these needs, even though we're looking at it likely a deficit in phosphorus And so we usually bump that requirement a little bit, or we match it with a soil test. So lastly is potassium. Potassium is absorbed as K+, and it's one of our base cations. And what we use for it is osmotic regulation. If you're familiar much with human anatomy, you would know we have sodium potassium pumps in our body that work for muscle movement, and that allows us to, allow different ions and solutions in. It's a lot similar to that in a plant because they use that to allow water in and out of cell walls. And it's very key in enzymatic processes in these plants that let them synthesize proteins that are involved in the nitrogen management. And so that's why we see this, it balances nitrogen management and use efficiency because of its effect in enzymatic processes. Again, it helps with that cold tolerance. It allows us to have better water efficiency. And anytime we look at plants, say like a grass or a corn plant, potassium is what builds those things tall. And so we use this term lodging, and that's the ability to resist falling over. If you've ever, our folks in the Midwest should probably be pretty familiar with the term lodging, or even down into Texas. If you look at a field of wheat that's had too much nitrogen put on it, or you've had some overlap, that's a very common thing to see, is because it gets too tall and it gets too heady, and then it falls over. And so good potassium helps keep things upright and erect in our grasses and in our crops. When we're deficient, we see this marginal kind of yellowing that results. It's almost a scorched look. Whether it's a legume, you see it this way, almost an inverted V of green comes in along these edges. And so one of the concerns that we do see here is when we're looking at reclaimed land, salt damage looks very similar to this. Or if we start to see a lack of water, they can be very similar in look. You would typically see more necroses, but again, this gets you in the right idea. So potassium management, it is going to move more, but again, it's less important. But we can see some leaching losses when we're talking about potassium, just because of its base cation and its ability to be leached out if our CEC isn't high enough, if we're in these very sandy soils and we can't hold it where we need to. So the last section I have, I've probably bored everyone enough with my talk on grass, but we have to plant a crop that makes sense, right? So this pipeline, this is probably, we're looking at a very wet area down in here. We don't have a tremendous amount of topsoil along this side. This is probably not the best place to plant alfalfa our first year, right? We know that if that's what they wanted to do. And so this is where I really say, talk to someone with extension, talk to an agronomist of some sort, let someone with some experience work with some of these producers. And we've worked with that in this area as to, what can happen if, so if you were out with the farm last year, that's what Tim had done, was talk to some people that would know more about what could be planted on this that would make more sense. And so that's very helpful. And so what we do is we look at these charts that say, what is the optimal normal growth range for alfalfa and what's its optimum. And so we know that if your pH is going to be between 5.8 and 6.2, you don't want to grow alfalfa, right? It's not going to take, it's not going to start. But you may be able to do a grass. You could get away with a corn, but we have to play with the hand that we're dealt. Regardless of what situation we're in, we can't make something happen that isn't there. And then that's when we end up kind of pushing against each other, is because the soil is the soil, right? These are very raw soils. They need time to heal. And that's the objective here, is to plant something that's going to work. And so we look at these other things about seedling vigor and their ability to persist, and how they'll deal with drought or wet. And so if we're looking at something, I mentioned reed canary grass in wetter areas. So it's got a high persistence in drought and a high persistence in wet soils, and it'll tolerate a low pH soil. But the issue is it's not a strong seedling. And so it's not going to compete well. So what we don't want to do is put 30% of this with a mix of 70% tall fescue, because we have such an aggressive seed that's going to overplay this reed canary. And so we have to be careful about looking at the mixes that we choose, how we plant these things, But tools like this are a fantastic way when we start making any of these sort of recommendations for mixes to know where we go. When we look at things, the big thing up here, and everybody has their favorite grass, right, is orchard grass. But when we're looking at something for, these areas that are going to be susceptible to drought because of drainage and wet and low pH and a persistence to these conditions, that's probably not the most favorable grass that we could go with, right? Because it's not that great in those categories. Or Kentucky bluegrass, where we have mediums and stuff in a low, where we should be more in this tall fescue area. Now, again, those are some diagnostic tools, and we use the same thing with alfalfa and the clovers and bird's foot. Bird's foot's a very common one to use in a lot of these reclamation projects. The downside is it's very difficult to start. Once it starts, it's very, very good to take off. It's very hardy in the winter. It's very good to kind of run by itself and take over and fight erosion. But it's not easy to just go out there and throw a handful of bird's foot trefoil seeds and come back with a stand. So this is the stuff that really helps us kind of make decisions. The last two tables is looking at seeding rates and how these things can play a difference. I don't know how many times I've looked at something that's been seeded and they say, well, I had a rate, I got alfalfa and white clover and orchard grass and timothy, but the rates that are used aren't adequate to make something work. And so, there's 200,000 alfalfa seeds per pound and 700,000 white clover seeds per pound. We certainly can't use 2 pounds of each and expect to have the same result, right? So we have to be aware of, when we're mixing or when we're developing a mix, how much percentage, how many of these seeds are in each of these bags, so that we can kind of say, all right, I need 6 pounds of alfalfa and 2 pounds of white clover. And then likewise for the grasses, right? If we're going to do some reed canary, we want to be 6 to 8 pounds of reed canary and 4 pounds of tall fescue, because there's a competitive nature there that we have to understand. So lastly is looking at mixes and use of annuals. If we have a situation where all we're trying to really do is get some cover, annual ryegrass is fantastic for that. If you're somewhere where you can get a drill in there and you can drill, open up the ground and place a seed or plant it, oats work fantastic for those. A lot of times we would refer to those as a nurse crop because they help fill in some of the area. They're going to keep the weeds down. They're going to get the cover there. They're going to keep animals and birds from getting to the perennials. And so we often mix those with a perennial plant, and that's going to give us the long-term growth. We're going to see that quick jump of the annual, so that we can say, all right, we've got the grass here, but that's going to appease the other side of what we can do to go long-term. And so when we're looking at something like that, we generally would look, 20, 30, 40% annuals with a, 60 to 80% perennial, so that we can get these mixed together. We're going to plant those in the fall, somewhere like September-ish. At least in this area, right? Everybody's going to have their own planting dates, and that's going to push us to where we're going to have good grass going into the fall. And then in the spring, we would then return with these better developed perennials to make this fit. So, I did have some help, and I pulled some old files that I had. And, so last, I think it's important for us to know what works, because everything's going to change, right? If we don't know what we're working in, it's impossible to not have compaction, but we want to try and limit it. Buy a penetrometer, give it a shot, see what happens, and plant a species of crop that's going to grow, right? If it's not going to grow, it's never going to help. And I think long-term, we need to look at what we can do to fix these things, to make it better for the producer, to make it better for the company that's doing it. And we just, everybody is much happier when these sites are left suitable, they're left clean, and they're left with a good crop. And so I think, at the end of the day, it's planting something that works. Work with an extension person, work with someone at a university. That's what I'm paid to do, is help make these kind of decisions. So I can take some questions. I don't know. I think I've got 3 minutes left, so I used my time well. I can stop sharing.
Your timing was perfect, Justin, and there are 3 questions. I don't know if you're able to pull up the Q&A pod. I'll just let you look at those and respond accordingly.
And
So,
if you could, I just put up a poll. If the attendees, could you please take a moment and fill out the poll? Thank you.
Okay. What happened with my slides? They weren't bigger.
I think it was just the presenter mode.
I'm sorry, folks. I'm sorry. Okay, so would you prefer to use milkweed or other pollinator plants? So, I like the use of pollinator plants and milkweed. I think that's a fantastic thing to do. And for me, that makes a lot of sense, right? When we're looking at things in forested areas or adjacent to fields, I really like that. In this area, we're really fortunate to have a lot of these companies and a lot of national and local attention on developing pollinators. And so it's really easy for people that are, if they're wanting to work in the pipeline or if they're a landowner that's going to do that, you can work with, I'm on a grant actually with the Audubon Society that does pollinator stuff. And I think that's a fantastic thing. So the hard sell that I have is, so, majority time I'm an agronomist and I spend 50, to 100 calls a year trying to, tell people what herbicides to use to get pollinators and milkweed out of their pasture fields and stuff. And so that's a very difficult sell. I try to make that sell and I encourage it whenever possible because even in cropping situations, there's been a lot of research done that shows even with self-pollinated plants like soybeans, there is a tremendous amount of yield bump we can see by having pollinators in the area. And so I try to do that as much as possible, but again, it's really hard to get people to do that. Okay, so I'm looking at the next one. So John, I may let you look at the next one because I think ideally what they're wanting to do is topsoil would go back on top. But we don't always have enough topsoil, right? So that's the problem we see in Pennsylvania is, when you scrape 2 inches of topsoil off with a field, it's very difficult to always put 2 inches back. And so regardless of what you're doing, you can take 2 inches off and put it over here, but as you've unconsolidated that stuff and you've put it back and you try and pack it down, it becomes very difficult to just, spoon feed 2 inches of topsoil back into place and then seed that. And so as those horizons mix, that's not ideal, but that's when the importance of looking at these nutrients and the organic matter and getting these things put back in place really makes the difference. So,
yeah, and Justin, I thank you for that. I think I'd say as you said at the beginning, we've got a lot of experts on here, and I think the answer may be dependent on the state or region where you're in, that what those regulations might be. So maybe some of our experts online here that are still participating with us might go into the chat pod and put what they know from their state or region. That'd be very helpful. And I know that we're a little bit over time. If you want to hang in, Justin, do you want to go ahead and ask that or respond to that last question?
sure. So I've got a couple more here. Could you say?
Oh, yeah.
So Deep rooting grasses, right? So all of our grasses are going to be deep rooting. And I'm not sure exactly where you are. So that's where it gets a little difficult having this type of webinar. You know, when you have people all over the country and even North America to even make a recommendation on, you know, deep rooting, things like that, is because we don't know. You know, I can make a recommendation for where I am, but that does help, certainly, right? So what we want to see when we're really looking for any of that is to have this mix. And so it's not always one species of grass or one species of legume or something. It's when we have that biological diversity that we really start to see things get much better, because we'll have certain things, you know, and I can speak to like an orchard grass that's going to go a little deeper and it's going to have more hair roots. And then you get more of a bluegrass that's going to be more of a shallow rooted thing. And so when you get into these deeper rooted and more shallow rooted, and you have this biological diversity in those grasses, that's when you start to see more of that minimizing of slumps and slips. And so that truly, to me, is the best thing to do. Is not so much of the one rye or the one crown vetch or something like that, but rather having something that's going to shallow root, something that's going to deep root, something that's going to laterally root, and mix that cocktail together, so that you're really looking at this of all aspects to hold the surface, to hold the depth, and to hold these medium things in place. And so then there was one on biochar. You know, I don't know much about the use of biochar in reclamation site soils. There's some bio-use in, there's some places around here that use biochar in their agricultural soils. And there's a lot of research and things that claim and show the amount of water holding capacity and the amount of nutrient holding ability that comes out of this. But so one of the issues that we have seen and I have heard at talks is the facility and kind of that infrastructure to make biochar, even for the agricultural community and the people that would like to mix that. So, you know, to speak on reclaimed stress soils, I don't know much about to that end, but I do know you're talking about a tremendous amount of char to get something in there to be able to till that into a point to where you could boost an organic matter, you know, 1%, because you're talking about 2 million pounds of soil in the top 6 inches. And it's not just a, you know, 1% of 2 million pounds to give you 1%, right? You've got to get that in there, allow that to break down, and then get the humic acid out of it. So it is a significant amount of soil and a significant amount of char. So I think that was all of them. I do apologize for the slides. I wish I would have. I did not have the chat pod open. I do really apologize for that. And if John wants me to, I can redo the talk and we can re-record it sometime and send it out to you guys again.
Well, why don't you just stay right there and just do it all over again?
Yeah,
Justin?
I can do that.
No, I'm kidding. No,
It's Thursday afternoon and it's raining, right? I may as well.
And it's raining. It's
Yeah.
raining in Western Pennsylvania. Justin,
Who knew?
Thank you very much for that presentation. It was fascinating. You had a lot of good information, and I suspect there'll be people going back to look at some of those slides to gather up some information. So thank you for your expertise and willingness to. I'm sorry about the stress and nervousness prior to today's webinar that you experienced, but we appreciate what you did today.
Well, I started with 150 and I ended with 130, so I think that's pretty good numbers. I'll live with that.
Hey, folks, thank you for being with us today. If you'd like to join us next week on Tuesday, Tom Murphy, who some of you know, will be joining us for biosecurity for on-site oil and gas infrastructure sites, disease, pests, invasive weeds. He's done a bunch of work with this. Not just in the States, but internationally as well. I think you'll find it interesting, and if you've seen some of Tom's presentations in the past, you know it'll be an interesting topic as well. So once again, thank you. We look forward to seeing you next week, and have a great day all. Thanks again for joining us.